Melting, freezing, and sublimation. So if we think about a solid and we increase the temperature, that's increasing the thermal energy of the particles. So they're moving more and more rapidly. They get to a point of increased energy where they're actually able to break away from those forces that are holding them together, and the substance will melt. The solid turns into a liquid. So here's the solid ice, and as the temperature increases, the intermolecular forces that are holding these molecules in this crystalline pattern here break, and it forms a liquid. The same thing happens in this state transition as does with the liquid to gas, where we get a flat place in the heating curve. When you melt the ice, once it starts melting, the temperature stays the same. All of the energy that you're adding goes into energy needed to break the bonds in the remaining ice. So anytime you have ice and water, well, I did have ice and Rockstar, you've got 0 degrees Celsius. It won't warm up until all the ice has melted. Yeah, I just said that. So here is another heating curve. It looks a lot like the one we saw for boiling the water, but the temperature range here is different. So here we're starting at minus 20 degrees, where we've got ice, and as we increase the temperature, adding heat, it gets to 0 degrees Celsius, the melting point of water, and the temperature flattens out. We add heat, we add heat, we add heat, it stays flat. All the heat that we're adding is going into breaking more of those bonds, those intermolecular forces that are holding the water molecules as a solid. Once they're all melted, all those are loosened up, then the temperature can increase. Is there a name for what? You mean for this part of the curve? No, I don't think there is. We could call it Joey. And maybe this would be Steve? I don't know. No, there isn't. At least not that I can think of right now. So you add ice to a drink to make it cool, right? To cool it down. How does it make the ice cool? How does it make your drink cool? As the ice begins to melt, it absorbs energy from the liquid, cooling the liquid. Melting is endothermic, absorbs energy. Freezing is the opposite, it's exothermic. So we understand that melting is endothermic. How do you melt an ice cube? You heat it up, you put energy into it. How do you freeze water? You pull energy out of it. What? How do you do that? Well, that's what your freezer's doing at home right now, hopefully. Ours went out this semester. We lived out of 2 dorm fridges for about 2 weeks. That was fun. Your freezer is sucking energy out of the inside of the freezer. Where is that energy going? Where is that heat going? Into your kitchen. You cannot make your kitchen cooler by leaving the freezer door open. Right? It's tempting. We also went a summer without any air conditioning, and we did stand in front of the freezer occasionally. But the process of sucking the energy out generates more heat. So, I'm sorry, I'm just in a very, very strange mood this morning. Do you ever have wet shoes that you need to dry? Seemingly unrelated things, right? Right on the floor in front of your refrigerator is a great place to dry your shoes. Because what your refrigerator is doing is it's sucking heat out of the inside. It's sucking more out of the freezer than out of the refrigerator. Where does the heat go? It gets blown outside, and it usually comes out along the floor. And so you stick your shoes right there, and you've got this very gentle breeze of slightly warm and very dry air, and your shoes will dry much faster, and you don't have to wreck them in the dryer. There's a life tip. Where was I? So the water in your freezer turns to ice. As that happens, it releases heat because freezing is an exothermic process. So that heat has to get sucked out by the freezer. And the process of refrigeration is another interesting subject that we're not going to go into today. So there's heat involved in that solid-liquid transition. This is called the heat of fusion. It's not called the heat of melting. Don't know why, but you've got to remember that fusion is melting. So I think of chocolate chips. You put a bunch of chocolate chips in a pan on the stove and you turn up the heat just a little bit. What happens to them? They melt. As they melt, they fuse together. Okay? So melting and fusion are the same thing. So the heat of fusion is how much energy it takes to melt a mole of the solid. So here's a mole of water melting from solid to liquid, 6.02 kilojoules. That's a lot less than it took to go from the liquid to the solid to the gas, right? That was like 40 kilojoules. Because when we're melting here, we don't have to completely break all those intermolecular forces, just partially. So it doesn't take as much energy. Delta H here is positive because melting is endothermic. Same amount of heat is involved when you freeze something. Going from a liquid to a solid, you have to extract, remove 6.02 kilojoules for every mole of water. Freezing is exothermic. So we can use the heat of fusion to figure out how much heat is needed to melt something, or we can figure out how much heat is released when something freezes. The heat of fusion works as a good conversion factor. So calculate the amount of heat absorbed when a 15.5 gram ice cube melts. We need more information. Well, we could go all the way back to a table, but we could just do it here too. Delta H for is 6.02 kilojoules. This is for freezing. This one's for melting. It's the same number, just the sign is different. So here we're calculating the amount of heat absorbed when a 15.5 gram ice cube melts. So we've got 15.5 grams, and we've got 6.02 kilojoules per mole. That's our heat of fusion. We want heat. Well, kilojoules would be a good unit of heat. So let's find kilojoules. Heat of fusion relates moles and kilojoules, but we need grams. So we're going to put moles in the middle. Moles often end up in the middle. And go grams to moles to kilojoules. You guys have gotten much better about asking me for help and asking questions. And I see people, they'll show me their work, and they don't have the path written down. If you're having trouble doing the problem, that means you need to write the path. Write the path first. And you might find that that solves most of your problems. Not all of them. Most. 15.5 grams times in a line. I'm going to put moles on that line. And I have another arrow. I'm going to put kilojoules there. Put the grams down here. Put the moles down here. This is the molar mass. Here we're talking about ice cube. It's water. 18.016. You can calculate that if you don't remember it. I don't expect you to remember it. And kilojoules per mole, that is the heat of fusion. 6.02 kilojoules per mole. So 15.5 divided by 18.016 times 6.02, 5.17, looks like 3 sig figs on this problem, and write down 2 extras, 92 kilojoules. So we'll round that to 5.18 kilojoules of energy absorbed to melt the ice cube. Any questions? So we've looked at 2 heating curves. Here is a full-blown heating curve for water. So here we have the temperature in degrees Celsius and heat added. So starting at minus 25 and heating this ice cube, we increase the temperature until it gets to the melting point. Then it melts, and once it's all done melting, the temperature will rise again until the water begins to boil. We keep putting energy in until all the boiling has finished, it's all converted to the gas state, and then the temperature will go up again. You should be able to look at a curve like this and have a basic understanding of what's going on. So correlate sections 1, 2, and 3 with the correct states of water. Well, section 1, what is the state of water in this section? It's going between a solid and a liquid, right? So this here is a mixture of solid and liquid. What about section 2? What's the state of water in that section? It's a liquid. And what about up here? We have a combination of liquid and gas, because that's the process of boiling.
Is that because gas turns to a gas at 100 degrees Celsius?
It begins to turn to a gas at 100 degrees Celsius, yep. Now, for different substances, the proportions of this will be different. The numbers, the temperatures at which these flat places occur will be different, but for most substances, the overall idea is the same. You take the solid, you heat it up. Once you get to the melting point, the temperature stops increasing until it's all melted. Then the temperature goes up again until it begins to boil. The temperature is flat until all has finished boiling, and then the temperature of the gas can rise again. Any questions? Okay, so seeing what's coming next, I need to say something else about this. So there's a lot of calculations that can be done in terms of water at different temperatures and going, through different processes. And so the next example is one of those types of problems. So what you do to approach those is you sketch a little heating curve and you identify, well, where am I starting? Am I starting somewhere down here where it's frozen? Am I starting here where it's a liquid? Am I starting at the melting point? Where am I starting? And where is it going? And then for each straight line segment that you have in that part, in that range that you need to deal with, you're going to have a separate calculation. And we've done both of these types of calculations now. So up here, you're going to use the heat of vaporization as a conversion factor. Down here, where we have the solid melting, you're going to use the heat of fusion. That's what we learned in this chapter. I think it was chapter 6? We talked about heating things up, and that's where Q equals MCAT. Q equals MC delta T. This is going to be the specific heat of liquid water. In this rising temperature portion, we also use Q equals MC delta T. and in this part down here. Anytime the temperature is changing, delta T, you're going to have Q equals MC delta T. So you do separate calculations for each line segment, and then you add them together. Yeah?
So for every time it's solid and liquid, you're going to use the H fusion.
Yeah, when you're in the process of melting or freezing, you're going to use delta H diffusion.
And then liquid is MCAT, and then liquid to gas vaporization. But then when it's increasing, it's always...
Right, when you have a single state and the temperature's changing, you use MCAT. When you're going between states, you use the appropriate heat of, either fusion or vaporization. So let's do an example. Calculate the amount of heat in kilojoules needed to convert 1 mole of ice at minus 25 degrees Celsius to water at 37 degrees Celsius. And we're given some information here. So I'm going to just draw an ugly little graph here so I can see what's going on. So I've got a mole of ice at minus 25, so we're starting down here at minus 25. And I'm going to water at 37. So up here I'm going to go to 37 degrees Celsius. So as I increase the temperature of the ice, it's going to increase until I get to what temperature? 0. At 0, it's going to melt. Right? So the ice is going to melt. Once it's all melted, then the temperature will increase again. And we're told we're just going up to 37. So that's below the boiling point, so we don't have another plateau on our graph. This is temperature. So I have 3 line segments, don't I? Means I have 3 calculations. So this one, let's call those, we'll call this A and B and C. A and C involve temperatures changing. So that's going to be an MCAT calculation. B is flat, doesn't involve a temperature change, but that's the melting of the ice. So that's going to use the heat of fusion. So I'm just going to start with A. So A, we're going to, because it's a slanted line, we're going to use Q equals MC delta T. So I need to know the mass. So I have 1 mole. So we need to calculate the mass. 1 mole of water, grams per mole. So the moles cancel out. This is the molar mass of water. You can maybe see how I have that memorized, right? I keep using it over and over again. Well, we don't really need a calculator for that, do we? 18.016 grams of water. So Q equals MC delta T. So Q for that section is going to be the mass of the water times the specific heat capacity. So here I have for ice and for water. This is the liquid, this is the solid. In this section, I have solid water, ice, heating up. So I need to use C for the ice. 2.09 joules per gram degrees Celsius. And what's the temperature change here for A? Delta T equals the final temperature minus the initial temperature. The final temperature is not the final temperature of the problem, it's the final temperature of the line segment. The final temperature is 0. The initial temperature was minus 25. So I'm taking 0 minus negative 25. The change in temperature is 25 degrees. It's a positive number because the temperature went up. Minus 25 is colder than 0. It went up 25 degrees. So I do the math there. 18.016 times 2.09 times 25. 941, and that should have 2 Sigfigs, 0.3 joules. Any questions? Yes?
You said minus 25 went up, so it became positive.
We went from negative 25 to 0, so that's an increase in temperature. So you can think of it that way, or you can do the math. 0 minus negative 25, those negatives cancel each other and make a positive. I don't want to round this off yet because this is not my final answer. I'm just going to leave it there. Let's look at B, segment B. Well, there's no temperature change. So if you try to use Q equals MC delta T, the temperature change is 0, and you're going to end up with 0, and hopefully that'll say, wait a minute, that wasn't the right thing. We want to use this heat of fusion as our conversion factor. So to calculate the heat here, I need to start with moles instead of kilojoules, if I can. I was given moles, so I'm going to do that. 1.00 moles, and I'm going to put the heat of fusion in here so that moles are in the bottom and kilojoules are on the top. 6.02 kilojoules per mole, and so that ends up being 6.02 kilojoules. Yes?
On an example, would we be given the HP?
You would be given these, yes. Absolutely. So any questions about B? The flat places are using the heat of fusion or the heat of vaporization as a conversion factor. There's not really an equation. For the sloped portions, Q equals MC delta T. The mass of the water is the same, 18.016 grams. The specific heat capacity, now this is liquid water, so I want to use C for water, not for ice. 4.184 joules per gram degrees Celsius. And then I need the temperature change. So for C, delta T is final minus initial. The final is 37, the initial is 0, and so that's just 37. The common error that students make is they look at the overall temperature change. You have to look at just the line segment that you're calculating. Each segment has to be calculated separately. So that's 37 degrees Celsius. So 18.016 times 4.184 times 4.184 times 37. 2789 joules. Questions? We're not done yet.
Like, I would try and subtract 37 degrees Celsius from negative 25. I would try to
Yeah, you would try to do this difference?
yeah, I would do.
Yeah, that's a very common mistake. The thing is, we are looking at just this part. So just that segment, and so we're looking at this temperature and that temperature. So that's something to watch out for.
And then you add the 3.
Yeah, so now we have to add the 3 together. It's asking for heat in kilojoules. This one's already in kilojoules. These are both in joules. So something has to get converted here, right? So I'm going to take my my joules here, and I want kilojoules, so I'm going to divide by joules. Kilo means 10 to the third, so 1 kilojoule is 1 10 to the third joules. So this ends up being 941.3 kilojoules. And keep track of the sigfigs. This one's okay by itself. It's already in kilojoules. And then this one, I need to do that same conversion. 1 kilojoule per 1 times 10 to the third joules. And so this is going to end up 2.789 kilojoules with the 7 underlined. So let's make a little space, go over here, and stack these up. So I have 0.9413, and I have 6.02, and I have 2.789. It reminds me of the 789. I already told you that one, though, so I'm not going to do it again. I'm trying really hard not to. 0.94, can't read, 13, plus 6.02, plus 2.789. 9.7503 kilojoules. Just a review of Sigfig rules. So we're adding here, and so I have uncertainty in the tenths place, and for both of these, it's in the hundredths place. So this is the first column with uncertainty, so I'm going to round my answer to that column, the fewest number of decimal places. The 5 tells me I have to round up, and so I'm going to report my answer as 9.8 kilojoules. Any questions? Yeah.
I think I would be tempted to, since you put 2 of them already in joules, just add those to it, and then convert that.
You could certainly do that.
Because I got the same answer, just wanted to make sure I could.
Yeah, you could take the joules, the 2 answers that are in joules, and add them together. Take that sum and convert that to kilojoules. You could do convert the kilojoules to joules, add them all together, and do it that way too. Any other questions? So sublimation is something you may or may not be aware of. It's a physical change directly from the solid to the gas. Now, a lot of things won't do this, but some do. So when the substance sublimes, molecules are leaving the surface of the solid and going directly into the gas state. They have to leave from the surface, though, because that's where they're held less tightly. Dry ice is a substance that does not melt. It's solid carbon dioxide. It does not melt at atmospheric pressure. So, that's why we call it dry ice. It's cold like ice, it kind of looks like ice, but it never melts, so it doesn't make a mess, right? It doesn't get things wet. It just goes directly to the gas state. At minus 78 degrees Celsius, the carbon dioxide molecules have enough energy to leave. Dry ice is really, really cold. Bless you. So here's dry ice. It looks like something's going on down here, right? What is that? So this is really, really cold, and cold air tends to fall. So it's cooling the air around it, and what it's causing here is it's causing the water vapor in the air to condense and form like a miniature cloud there. So this is not dripping of the solid or the melting of the CO2, but that's condensation we see from the cold air. The solid CO2 will just gradually go away. It won't melt, not at atmospheric pressure. You can make it melt at really high pressures, but not at atmospheric pressures. At no temperature will it melt. Yeah.
So it's like equivalent of evaporation for?
It's evaporation, but it's skipping the liquid. Just skips it. And some substances do this, most don't. Most will melt. Yeah. I know, it's kind of a weird thing to get your mind around. Ice does melt. Ice also sublimes. It can do both. Regular ice will slowly sublime. It doesn't sublime as fast as CO2, but it will slowly sublime at temperatures below 0 degrees Celsius. If you get it at 0 or above, it's going to melt, but below 0. So frozen water will gradually turn into a gas. So have you ever found something in the back of the freezer, maybe an old ice cube tray or something, and the ice cubes are small? How did the ice cubes shrink? How does that happen? It's sublimation. The ice in your freezer is slowly subliming. Now, if you're using your ice regularly, you don't notice it. This also explains freezer burn on food that's kept in the freezer too long. Because the water present in your frozen food can sublime. And if it's uncovered, it will happen faster. If it's in a loose sealed bag, it will happen slower, but it'll still happen. So you pull out an old bag of tater tots and you dump it out on the pan to cook it, and there's all these ice crystals. Like, who puts ice crystals in a bag of tater tots? Well, they didn't put them in there. That's water that used to be in the tater tots. It's sublimed. It went from frozen to a gas, and then it's in this bag, and it's doing what gases do, going in a straight line till it bumps into something. Eventually, I mean, it's cold in there, so it's going to lose energy. It'll hit another water molecule, and ice will start to form, and gradually the water that was in your food moves out of your food. You can reduce that in two ways. Buy an expensive freezer that is super cold, because the colder your freezer is, the less sublimation occurs, or seal your food with very little airspace. So that's the appeal of the vacuum sealers. Suck all the air out. If there's no air there for the water to sublime into, it's going to have a lot harder time escaping. I just did all that. I told you, I get ahead of myself all the time.